Well, howdy there, Internet people. It's Professor Leach again. Today, we're going to continue talking about operations. And just like we started off with yesterday, we're going to say now with polynomials. I don't want to smear all this. Now with polynomials. All right. So once again, I want to look at operations on numbers and compare them to polynomials because I really want to get at understanding what the operations are about so that we can recognize that we're just doing the same thing. We're not doing anything new. All this polynomial operation stuff is still just the distributive property, and it's based around the fact that this multiplication distributes over addition. So I wrote a quick summary. The summary started getting out of hand, so I'm like, oh man, I just got to start class. So let's review. Addition has some simple rules. This includes its inverse subtraction. We only add or subtract things that are the same, and when we add them or subtract them, it doesn't change what they are. This idea is, the idea of sameness varies depending on what we're looking at. When we're just adding numbers, place value is the sameness that we use. When we're adding fractions, denominators is the sameness that we look for. Out in the, quote, real world, as if it's some separate thing from the mathematical world, dollars and dollars we can add together. And when we add them together, it doesn't change what they are. Then we went on to multiplication. That's one level above addition. Mostly because multiplication represents repeated addition. That's what we use multiplication for. It's like if we're adding a bunch of things that are the same, let's summarize that with some multiplication. Then we have to come up with some notation for that. We, like I was there. So we decided that x plus x plus x, we wanted to communicate, that's just 3 times x. So let's write it this way, 3 right next to the x. And then we'll all just understand that means multiply the 3 by the x. And then someone's like, oh, are you sure everybody's going to understand that? And you know, people were like, oh, yeah, I'm sure it'll be fine. And I go, yeah, it'll be fine. And then, you know, like 1,000 years later, it's like, oh, it's kind of not fine, but we're working on it. The coefficient is a number written on indicating the repetition written on the left, and it's the same on the same line as the variable, and it's the same size as the variable. So they're written together. So we just write 3x. The left side of the variable is reserved for what we call the coefficient. It's a constant multiple that we stick out in front. Now that we've got this operation of multiplication, we have to decide how it interacts with addition. What if I've got a multiplication and an addition together? And one of the ways they interact is that multiplication distributes over addition. And so that's the distributive property that we've been playing with now with polynomials. One of the things I wanted to bring up today, is something that I just kind of like did in previous days. We start off, if we think about multiplying the 20 plus 3 and the 10 plus 7, or all the cool varieties that y'all came up with in that discussion, which was very cool. I know it was a really weird thing to ask for, but it really kind of, I hope that it drives home the problem of this multiplication business. The standard algorithm is just trying to get you to do this, multiply each digit of one number by every digit of the other number. That's why I wanted you to go this way instead of going back to 23 times 17. I wanted you to do it in some weirdo way. This one isn't weirdo. This is just bog standard. But we get to this part. We get the 2x times the x. And that we write that as 2x squared. So this is where we start getting into repeated multiplication. And for repeated multiplication, we use exponents to denote that. So 2x times x is 2x squared. We're usually presented with this is that when you multiply things with the same base, you add the exponents. But that shouldn't be a standalone thing as a, quote, property of exponents. Of course that should be what we do because of what the exponents represent in terms of repeated multiplication. The other thing that I wanted to include with the multiplication before I got excited by all these distributive property problems. is that multiplication goes before addition. Multiplication before addition, unless parentheses. Take PEMDAS and chuck it out the window. PEMDAS is trash. Parentheses aren't an operation. They're a signpost to say, do something else first. I don't want to include it in our order of operations because here are parentheses. And the order of operations says, do this first. 3 plus 7 is 10. 5 times 10 is 50. But we clearly don't have to do it that way. This 5 parentheses 3 plus 7 close parentheses also means 5 times 3 plus 5 times 7. What if we want to use the distributive property and come up with 50 that way? Not because it's faster or better, it's just different. But PEMDAS says, no, thou shalt do this way. PEMDAS is wrong. Not that it's going to give you wrong answers. It's morally wrong. So also when we see these parentheses here, there's nothing to do with the x plus 7 because of rules of addition. We only add things that are the same. And in polynomials, sameness is like terms, same variables with the same exponents attached. X and a 7, I can't add those things. So in one sense, this is simplified. So when people say simplify this expression, you should be asking like, oh, well, what do you want me to do? But if I say multiply, then you're like, oh, well, distributive property tells me that I can multiply. This multiplication will distribute over this addition. 5x plus 5 sevenths is 5x plus 35. Just like if you said 5 times 17 will be 5 tens and 35 ones, 85. Because it's all the same. So multiplication before addition, unless parentheses. Multiplication represents repeated addition, and we denote that with coefficients. And multiplication distributes over addition. Any question? Scroll. Then the other operation that we have are exponents. We haven't talked about the inverses of the exponents. Their inverses are other exponents. We undo an exponent with another exponent. Sometimes these other exponents are denoted with radicals. So if you're familiar with things like square roots, you're already familiar with the inverses of exponents. A square root is the inverse of a square, and it represents another exponent. So we want to learn to read radicals as exponents. It's very archaic. I don't know why we still have radicals. I think we still have radicals because we've always had radicals. And it's one of the things in math. It's like, well, we've always done it this way, so let's just keep doing that. It's like, well, that's never a good way to run a thing, but all right. So exponents have things that we can say about them just like multiplication. Exponents represent repeated multiplication. Exponents represent repeated multiplication. But we denote them with, well, exponents, superscripts on the right side where they're written smaller and up. So we denote them but if I have x times x times x, I write that as x to the third. The exponents is a number on the right side, but it's a superscript, which means it's smaller and up. Or we can denote it with the exponent button, x to the third. If we use the to the button, we don't have to write the 3 as a superscript. So superscript or on the same line with to the. So it's just an arrow pointing up. That's also the way I write n, which is very confusing sometimes. So I have to emphasize the pointy, almost capital lambda look of the to the button. This is less common, and I hope it gains more acceptance. But as you can see, we've got operations on the. Here are the number keys on our calculator, and here are operations plus, minus, times, and divided by, and they're highlighted with this light gray. Meanwhile, the exponent key, which is also an operation button, is like, no, that's like with the rest of them. Like addition, subtraction, multiplication, division, they're like, oh, yeah, we're operations, but you, exponent key, you don't get to be part of this light gray stuff. You don't get to be highlighted. We're going to make you more difficult to find. It's like, is that not an operation in Texas or what? I think it's because they want this part of the calculator to look like an old style calculator. And I think what they don't realize in Texas is that old style calculators where it's just these 4 operations are really hard to find. For the most part, this is what calculator looks like. And they even try to hide it on your iPhone calculator. I don't know why. Because I feel like when you first open your iPhone calculator, they're like, oh yeah. Addition, subtraction, multiplication, and division. And then that outdated percent key, because we don't actually want to understand how percents work, we just want a percent button. Meanwhile, if you turn your calculator sideways, it's like, oh, there are the rest of the buttons. And it takes the exponent key and it writes it in this really weird fashion. It's like no one does scientific calculators like this anymore. At least they have parentheses keys. All right. So exponents represent repeated multiplication, and we denote them with superscripts or to the. The thing is, we need something to denote repeated addition. We put that number on the left and call it coefficient. We needed something to denote repeated multiplication. We put that on the right and call it exponent. Cool, it's all very organized. Also, exponents distribute over multiplication. Whatever it's repeating, it distributes over that operation. So exponents denote distributes over multiplication. Just like multiplication distributes over addition, the one level below it, exponents distribute over multiplication. The operation distributes over the thing one level below it. So now this one we don't get as much mileage out of, but what that means is that if I have, say, 2x to the third power, I can write that as 2 to the third power times x to the third power. I wouldn't write 2 to the third power unless I really needed it to be in pieces. I would usually write that as 8, but it's still x to the third power. Everything in the parentheses gets to the third power because I distribute the 3 over the product, over the multiplication. Any questions? This is fine. This exponents distribute over multiplication is great when we just have one term. If I have more than one term, that becomes addition, and exponents do not distribute over addition. I didn't write exponents distribute over addition anywhere. Did I? Nope, doesn't look like it. So if we had x plus 2 to the third power, I can't just say x to the third plus 2 to the third, because that's distributing over addition, and exponents do not do that. So I ain't even gonna write it down. Also, I ran out of space to fit it. Any questions? Comments? So here's our summary page of the things that we want to remember about addition and multiplication and exponents. I really just wanted to record this scrolling up and down for some reason. So one of the things that we talked about yesterday and that I want to reinforce today is that exponents do not distribute over addition. Exponents do not distribute over addition. You may have noticed that I want to highlight this do not part. Exponents do not distribute over addition. This goes back to us not really reading what's going on and just looking at things that are similar and trying to make it fit where it doesn't. I don't know if I've emphasized this enough. I'm glad I'm recording this whole thing though. It's going to make for some thrilling YouTube later. Exponents do not distribute over addition. So if we have x plus 3 squared, we can't just say x squared plus 3 squared. I have to read this as 2 copies of x plus 3. I have to read this as x plus 3 times x plus 3. So if I say perform the indicated operations, I want you to take the x plus 3 and I want you to square it. You need to read, this is an exponent, and it says multiply, repeated multiplication. Take 2 copies of x plus 3 and multiply them. That's what the expression is telling you to do. Take 2 copies of x plus 3 and multiply them. Then when you look at this product, you say, and this is where the distributive property comes into play, where each term of one polynomial gets multiplied by every term of the other polynomial. I want x times x plus x times 3, I write the coefficients first, plus 3 times x, because there's 2 versions of that, plus 3 times 3. When I multiply x times x, I get x squared, not because of rules, because that's what x squared means. It means 2 copies of x multiplied together. So I'm going to summarize that with x squared. I have 3x and 3x. Those are like terms. These are x terms. These are x terms. In polynomials, like terms is sameness. Like terms is sameness. And like terms means same exponent, same variables with the same exponents. So this x squared is not like these others because it has a different exponent. So plus 3x is plus 6x. Because I have x plus x plus x plus another x plus x plus x. There's 6 of them total. And then 3 times 3 is 9. Notice we can't just square the x and square the 3. We'd be missing out on that 6x in the middle. And if we're thinking, that's dumb, why don't we just use the distributive property here? The answer is, that's not how numbers work. Compare x squared plus 6x, x squared plus 6x plus 9. If I want to multiply 13 squared, that means to take 2 copies of 13 and multiply them. And when I multiply 2-digit numbers, I have to make sure that each digit of one number gets multiplied by every digit of the other number. And we can set that up in the same way. That's a 10 times a 10 plus a 10 times a 3 plus a 3 times a 10 plus a 3 times a 3, or a 100, 6 tens, and 9, otherwise known as 169. If we just square the 1 and square the 10 and square the 3, we're missing out on the 60. So we don't multiply x plus 3 squared this way because of rules. That's how numbers work. It even looks the same because I picked 13 and not 15. But it works for the bigger numbers anyway. Let's suppose that we looked at, so this one worked out because, right, 3 times 3 is 9. Everything fit into one digit. What if it doesn't? What if I wanted to say take 2x minus 5 and square that? Same thing applies. I can't just square the two things, the two terms, because this is addition. Exponents do not distribute over addition. I need to write 2 copies of 2x minus 5 and use the distributive property to multiply them. So I have 2x times 2x. I'm going to write it out. That's my thing today. 2x times negative 5. Oof, I'm going to run out of space. I'm going to have 2x times a 2x. And then I'm going to have a 2x times a negative 5. Then I'll have a negative 5 times a 2x. And then I'll have a negative 5 times a negative 5. I've used the distributive property. I could not distribute the exponent over the terms, because that's exponents do not distribute over addition. Do not distribute over addition. So I write 2 copies of 2x minus 5, and I use the distributive property to multiply, because multiplication distributes over addition. Each term of one polynomial by every term of the other polynomial. 2x times 2x, well, I can just multiply all that stuff. 2 times 2 is equal to 4, and x times x is equal to x squared. I'm just gathering things with the same base. 2x times negative 5 is negative 10. 2 times negative 5 is negative 10 times an x. Negative 5 times 2x is a negative 10 times an x. Negative times 5 times negative 5 is positive 25. These two things in the middle are equal. So I can write this as 4x, or not equal, sorry. Well, they are equal, but they're like terms is what I care about. So I can add them. I can't add this x squared because it's a different exponent. But I'll combine my like terms because I add things that are the same. And when I added them, negative 10x minus another 10x, it didn't change what they are. Now, if you're wondering what number I'm looking at here with 2x minus 5, that's just 20 negative 5 in numbers, if x is 10. And that means 15. If I take 15 squared, that's 15 times another 15. And I don't just square the 10 and square the 5 and add them. That's not, that's not how it works. I have to multiply each digit of one number by every digit of the other. That's what the algorithm is trying to get us to do. So I have a 10 times 10 plus a 10 times 5 plus a 5 times 10 plus a 5 times 5. The same 4 terms that I had up here. 10 times 10 is 100. 10 times 5 is 50. Another 10 times 5 is 50. Plus 5 times 5 is 25. So we get 100, 225. We might have just known that. I might have said 15 squared, and you just said 225 because someone programmed you with the, either someone programmed you with the squares all the way out to 15, which is pretty cool, or you just did it really fast. And you're like, well, why don't I do it my way? And I'm saying, do it your way. I'm trying to explain things. I'm not just trying to arrive at 225. I knew this before I even wrote down 225. I knew it was going to be this when I started writing this problem up here. I looked into the future, but it was the future of my own mind, so that's not really that impressive. Now you might notice that these don't really look the same until, if x is 10, this is 400, and this is negative 200, and 400 minus 200 is 200, plus 25 is 225. So that's pretty cool. But what's running behind all of this is that we didn't learn a new thing with these exponents and how they apply to polynomials. We're still just adapting an old thing. 15 squared means a 15 times a 15. And when we multiply 15 times 15, whether we do it in this weird Leachian way like this, or whether we just set it up vertically like we were programmed with as children, you're all doing the same thing. 5 times 5 is 25. 5 times 10 is 50. 10 times 5 is 50. And then 10 times 10 is 100. Still 100, 125, still 225. Maybe you didn't write it that way. Maybe you wrote 15 times 15. And you're like, well, 5 times, oops, I'm gonna run out of the room. Maybe you wrote 15 times 15 and you wrote it in this really messed up way because you were programmed with this really obscure stuff. And you're like, oh, 25. And I'm like, oh, all right, if you really want to write things that way. 5 times 10 is 50 plus 2 is, wait, 5 times 10 is 50 plus 2 is, 5 times 1. I forgot that when you set things up this way, you have to read the numbers wrong. 5 times 1 is 5 plus 2 is 7. This 75 is just 50 and 25. It's actually this 50 and the 25. And then you just do the 1 time, you put a 0 here, some of you do that. Then you do 1 times 5 is 5. It's really 10 times 5 is 50. And it's kind of like this 50 here. And then 10 times 10 is 100. So there's your 150. And this 75 is your 50 and 25. So no, you didn't do anything different. I know a lot of parents think that teaching things this way is bad because they learned it this way and they need to explain it to their kids. And I recognize that we're in a global pandemic and it's very unsafe to go back to school. But I think the most important thing that school children can learn right now is that when the safest thing to do for society is to stay home and not be in contact with other people, that's kind of what we need to do. That's the lesson right now. And if we have to wait to teach them how to multiply some stuff, let's wait. Because too often I see people saying, why don't you just do this? And the answer is because I want them to understand things. And if you don't want your kids to understand things, why don't you just pull them out of school? Teach them yourself. I mean, I'm horrified by what that would result in, considering you looked at an expert who said, hey, there's other things going on here. Let's take a look at that. And you're like, oh, no, as if not knowing something will make things better. I don't know, maybe they have a point. Ignorance is bliss, and that must mean that knowledge is suffering. So maybe we should all just stay ignorant. Anyway, what are we talking about? Oh, yes. Parents and why I don't teach high school anymore. I love the fact that your parents could call me and I just can't talk to them about your schoolwork. It doesn't matter if you were 12. If your parents call me, I have to apply the same rules. I would need some kind of explicit permission. You'd have to say, it's okay to talk to my mom. And your mom could be like, oh, I'm paying for their schooling. It's like, oh, well, that's really nice of you, and I'm glad that you do that. It's your responsibility to do that, so I appreciate it. But I'm going to need their explicit permission. And I don't care if they're 12 or 15. I'm going to respect them as humans. Tell you what, you want to find out how your kid's doing in math? Ask them. And if they won't tell you because they're afraid of you, ask yourself, why is my kid afraid to talk to me? And then do some introspection and stop blaming them for your failings. You know what I mean?
Deep.
In case you're wondering, no, I absolutely don't have children. But let me tell you why that it's better that I can think about these things. I'm not emotionally invested in justifying my existence as a parent. I can actually look at parenting rationally and say, you know what, there is no such thing as there's no hard and fast rules for good parenting. I accept that. But there are some pretty hard and fast rules for being a decent human. Anyway, what are we talking about? I went off the rails a little bit. But my parting shot, and if you're a parent, if you're a parent, I know and I hope that you're doing the best you can with what you have. I mean, not with what you have in the kid, with the kid. I mean, I just hope that you're doing the best that you can. But I think the most important thing is to come at the relationship with love and acceptance and understand that that child is your creation and it doesn't owe you anything. Just because you asked, you conjured it, it's your responsibility. It doesn't owe you anything. I don't care how old it is, it doesn't owe you anything. You know what I mean? Anyway, that's completely beside the point. I understand that being a parent is difficult. Not personally, because I only have a dog, and dogs are so much easier. You just like chilling out and sleeping. But anyway, I do know this. And if you're like, oh, don't teach my kid a thing, I am not gonna, I reject that wholeheartedly. Sorry, it's like literally my job to teach kids things. I know y'all aren't kids, but it's literally my job to teach people things. Otherwise, I wouldn't be called teacher, I'd be called not teacher. I hold things back, I keep secrets. Now, I don't do that. Go find someone else to keep your secrets. Anyway, it's just a thought. Y'all have a good day.